Get started. Welcome everyone to the Ontology Summit 2023. I'm Ken Balhoff, chair of the Ontology Board of Trustees. And today is February 22nd, 2023. And we are happy to welcome Jim Balhoff and Nico, who will be speaking about Ubergraph and other related topics. And now I'd like to pass control over to James Overton, who will be introducing our speakers. So, James.
Thanks, Ken. Yeah, I'm James Overton, and along with Gary Bergcross, I've been co-organizing this Ontology Summit 2023. And this first several weeks of the summit have focused on OBO projects and OBO standards and tools, just as like a springboard for jumping off and talking about ontology in science more generally. And yeah, we've been building up from our high-level ontologies like Cobb and the relations ontology, and then I presented on robot and Chris on the ontology access kit. We had a week on ontology development kit, and last week was on OBO dashboards and quality control. And this week we're going to kind of bring a whole bunch of these things together. First, Jim Balhoff is going to present on Ubergraph, which is a knowledge graph that brings together a whole bunch of OBO ontologies and really demonstrates the benefits of our degree of standardization. And then Nico Matanzoglu is going to present on SSSOM, or SISM, which is a mapping standard for connecting ontology terms or terms and data sets to each other, to ontologies, and is another way that shows how integration can really work at this scale. So Nico's presented a few weeks running now, so everyone should be familiar with him. He has a consultancy called Semantically and works with Mondo and EBI and a whole bunch of projects in our space. And and then we're delighted to have Jim Balhoff presenting. He's Assistant Director of Analytics and Data Science at Rensi. And Jim builds all sorts of great tools that our community relies on, maybe a little bit more behind the scenes than Nico and I, but completely fundamental to the stuff that we do. And I'm often pretty jealous of the stuff that he gets to build and the contributions that he's made. So Jim is going to start off talking about Ubergraph. Take it away, Jim.
Okay, so let me just share the window here. Thanks, James.
Your slides now.
Okay, great. So I'm going to talk about this project called Ubergraph, integrating OBO ontologies into a unified graph. And so what is Ubergraph? So there's two aspects of that I'm going to talk about today. One is that Ubergraph is a particular online resource. It's a database that you can query. So it's an RDF knowledge graph of OBO ontologies. And I think right now there are 53 of them in there. And it provides a public Sparkle query endpoint that anybody can make use of. You can build applications on that or just submit queries through a web query interface and explore it. And then also Ubergraph has a particular approach to rendering our ontologies as knowledge graphs, which is meant to be an ergonomic way to traverse and query ontology content and give you access to the actual logical semantics of the ontologies in your queries. And so I'll talk about that in the rest of the talk. And so why do we want an OBO knowledge graph? We have already the multiple ontology repositories online. There's like the ontology lookup service at EBI. There's OntoB. There's BioPortal. And so these provide repositories of numerous ontologies. They have even APIs. You can access ontology content that way. But I'm going to just talk about why it's kind of useful to think about the OBO ontologies as a unified knowledge graph. So the OBO mission is to develop a family of interoperable ontologies that are both logically well-formed and scientifically accurate. So interoperable is kind of the key word for me here. And so just an example, we have different ontology projects in OBO. There's anatomy ontologies. There's kind of one main chemistry ontology, KEBI. There's ontology of biological processes, which is part of the gene ontology. And so in actuality, these are developed, fairly independently and in a very loosely federated way. But actually, they all fairly tightly reference each other. And so, throughout the gene ontology, there's thousands of references to chemicals that are terms in the KEBI ontology, and also to anatomical structures that biological processes are taking place in. So there are all these mutual kind of cross references, and not just sort of mappings, but actual uses of each other's terms in their semantic definitions. And so one way that this is important is kind of handling classifications like this. So this is just a little snippet out of the gene ontology. There's different kinds of there's glucose synthesis, which is a kind of glucose metabolism, but it's also a type of carbohydrate synthesis because glucose is a carbohydrate. And so you have kind of a parallel classification with catabolism, like breaking down the glucose. And so a lattice like this, gets even more complex when you bring in all the other, ways you can classify glucose and classify different kinds of metabolic processes. And so it's very difficult and error prone to manually maintain like the ontology lattice like this. And so in actuality, there are some core hierarchies that are developed more independently. So gene ontology has this core classification that synthesis processes and catabolism processes are kinds of metabolic process. And then the fact that glucose is a type of carbohydrate, that's over there in KEBI, and that's stored in the chemical classification. And so in the gene ontology, really the way these terms are defined is with these AL expressions. And so carbohydrate metabolism is a metabolic process that has input or output some carbohydrate. We're using the actual KEBI term in the logical definition there. And so, all of these definitions follow the same design pattern or, a related one, whether it's input or output, but, they need to all align. And that kind of touches on some of the things that, James talked about, I think a little bit about robot template. And we have some another piece of software called DOS-DP tools, which is so for applying consistent logical patterns within your ontologies. And so if you do that, have consistent modeling like this, and then bring in the semantics from these external ontologies, then you can let the OWL reasoner just automatically compute this lattice for you. And so we don't need to maintain this in Go, and we just run the reasoner and then store the output and publish the hierarchy. And so, across OBO, we have this happening quite a bit. And so this is an example from human phenotype ontology, HP. There's a term astrocytosis, and in its logical definition, there are 4 different ontologies referenced, all just in one expression. So relations from relation ontology, some qualities from Pato, increase rate, abnormal, and then a cell type and a biological process from Go. And so, classifying this term in HP is like what the semantic meaning of this term is totally dependent on, what these other terms mean that are in this equivalence expression. And so, just as an example of the level of cross-reference we have, so these are some of the ontologies in Ubergraph, and on the left you have ontologies that are reusing terms from other ontologies, and on the right you have ontologies whose terms are being reused. And so the thickness is the number of terms. And so you can see in the top right, Uberon is an anatomy ontology that covers all of animal diversity, and it's very widely used in logical definitions of other ontologies. So you have the mammalian phenotype ontology, talks about abnormalities of different anatomical structures, and then also human phenotype. They're both pulling a lot of terms from Ubron. Gene ontology references it for locations of processes. The Mondo disease ontology talks about what structures are affected by a disease. Another one that's really highly reused is Kebi, chemical ontology. It doesn't really make too many, make outgoing references itself, but it is very widely reused. And then you can see the ones that especially Mondo is sort of using a pretty broad array of terms from different overall ontologies. So I think that kind of makes the case that it's useful to think of OBO ontologies as a unified, one big unified ontology or a knowledge graph. And so they're even though there's this kind of loosely federated development, the goal is to have this interoperability. And so let's say we want to build such a merged ontology knowledge graph. It is convenient that we use the OWL specification, and that's natively, OWL ontologies are natively saved as RDF, and RDF is a great format for merging things together. So we can just merge all these RDF files together into a triple sort database, and then it's all together. But that still leaves us with some significant challenges to actually using it. And so one of those is sort of syntactic challenges. It's when you just merge them together like that, you end up kind of querying what I would call ontology source code. It's not very user friendly. And then the other side of it is the semantics, that OWL ontologies are logical models, and you kind of need reasoning to actually use the full logical implications that they're giving you, kind of accessing all of the knowledge that's encoded in there. And so just to kind of look at these problems more directly, we'll look at like this gluconeogenesis term, which is glucose synthesis that I had mentioned earlier. And so some of you might not be familiar with the OBO file format, but I think a lot of people will. But it's kind of a simplified way to define ontology terms. And so this is just to show you, we have a Go term, gluconeogenesis. It has a text definition, and then it's a type of biosynthetic process, and it has output glucose. And so, well, a lot of people will think of this in this kind of graphical way, like down in the lower left. It's a very simple way to see it, and lots of bioinformatics tools are built on looking at ontologies from this perspective. We've just got a directed graph. It's got is a relationship to biosynthetic process, and it outputs glucose. And so, if you have this in a graph database, you might want to write a query: what processes output glucose? And if you are familiar with Sparkle query language, or even if you're not, you can look at the box on the top right. That would be how you might write it if you're just thinking about a simple graph perspective. So we have a variable process, and we're saying, which processes have output Kebi 17234, which is the glucose term. But that doesn't work by default. So in reality, if any of you have worked with ontologies at an RDF level, it's sort of a lot more complicated how the OWL gets stored in RDF. So really, it would be this pattern where you have some looking for some process, which is a subclass of existential restriction expression. So that's encoded with all these other triples. So it has output property and then some values to the Kebi term. But that's real pain to query things that way. And then in actuality, for this term, it's really more complicated than that, because glucose synthesis, it's defined with an equivalence axiom. So it's equivalent to the intersection of biosynthetic process and has output glucose. And so in OBO, the syntax actually looks like this on the lower left. We have these intersection of properties, but if you're querying with Sparkle, the sort of RDF serialization of it, you have this very complicated thing you have to write. So our process now has an equivalent class relation to this thing that is an intersection of a list. And so then you have to query the RDF list syntax using a property path. And then you get to the existential restriction. And so this is even worse. And so that's the sort of syntactic problems. And then what about the semantics? So if our question was which processes input or output any carbohydrate? Well, if we know the relation ontology, we might want to take advantage of the fact that there's a super property has participant, which covers both input and output. And so if we want to say, what processes have a carbohydrate as a participant, we might write it something like this down at the bottom, ignoring that equivalent class complication. So we could use a Sparkle property path to look, for a chain of subproperty to get any subproperties that has participants. So that would give us input and output. But then we also need to get any subclasses of the Kebi carbohydrate term, 16646. So we can use another property path there. So this might work in some situations, but then there's a lot more in the relation ontology. There's property chains. A chain of has part and has participant implies has participant. And the same thing with ends with and has output implies has output. And so it's really hard to try to encode this into your query. And there's transitivity of properties. And so at this point you really should be using an OWL reasoner. So we have a reasoner running. We could do a DL query and just say, give me all the subclasses of has participant some carbohydrate, and that should work. But so what we really need to do is a simpler way to create the stuff in our triple store. So we could use a reasoner in Protege, but that has a lot of problems for this situation. So if we're trying to bring together a big suite of ontologies, it's going to use a really large amount of memory, possibly more than a lot of people have on their personal machines. It's a really slow startup. You have to download all these ontologies and load them in, classify them. I think for the current Ubergraph, I think it's about 30 minutes or so, like just to parse everything and load it into memory with the OWL API. So that's not a great solution to just say import all of them into Protege. There are some triple stores that incorporate OWL reasoners into their software, but really most of those that I'm familiar with are typically focused on instance classification, kind of a more typical semantic web scenario where you have probably a smaller schema type ontology and then a large knowledge graph of instances, where it's not so much focused on terminology reasoning. Right? This use case for Obo is sort of a very large terminology graph, so it's kind of a different application of OWL reasoning. So what Ubergraph does is this pre-computed relation graph, which is a term that we've kind of made up for this situation to describe how we're pre-computing the inferences. So what Ubergraph does is materializes every implied edge between every named class as simple RDF triples. So the easy one is if A is a subclass of B, well then there's just a triple A RDFS subclass of B. So that's standard, but also it's not just the asserted ones, but it's every implied subclass relationship is also stored. But then for the more complex situation where you have A is a subclass of the expression R sum B, so that's that existential restriction like has output some carbohydrate. Everything kind of matching that structure, we also add a triple to the database just to direct A, R, B for gluconeogenesis, has output glucose. And so with just the idea that that's documented to mean the OWL semantics of that subclass of the existential relation. And so just to kind of spell out like what's in there, we kind of pre-compute everything. So for that gluconeogenesis example, it's a subclass of the biosynthetic process, but we're also going to have the triple that it's a subclass of metabolic process all the way up to biological process. So just exhaustively pre-computed. And then same thing, it has output glucose, has output carbohydrate, has output chemical entity. So, as general as you can get. And then same thing with every super property it has output, has participant glucose, has participant chemical entity. So all of these things are in the triple store, kind of ready for you to query with Sparkle. And so this is computed with this tool called Relation Graph, which is a freely available tool for computing ontology closures over any relations. So it's based on a reasoner called Welk, which is itself based on the widely used ELK reasoner. It uses the ELK algorithm. But Welk, it computes like generally the same inferences as ELK, but it has a very different performance profile. So it's slower for some use cases, but it's much faster for answering many consecutive and parallel DL queries. So that makes it very useful for pre-computing lots of query answers. And so it can for every property and class in the ontology, every possible combination, it computes every subclass of the expression R sum C, and outputs this sort of simplified triple representing the result. And so, for Ubergraph, it's sort of about 4 billion queries or so, but it doesn't really do all of them. It kind of has a smarter algorithm. And so it streams the output to an RDF file, and then we load that into Ubergraph. And so this functionality actually just got released a few days ago as part of Robot. It powers a new subset command that's in there, but it's also available as a standalone tool just for computing closures over relations. And so just some examples of what then you can do in Ubergraph. You might have a query, like I was saying before, what processes output glucose? And so you can write it in this much more simplified way. So some variable process has output, some particular heavy term, and then we get its label. And then you just get this result. There are two results, gluconeogenesis and this sucrose catabolic process with 3' ketosucrose. And so if you have the slides, you can follow this link to a query. You can run it on the YASGUI Sparkle query interface online. You can also do some things that are a bit more inconvenient or impossible to do if you're using a DL query engine like in Protege. So you could query the other side of existential restrictions. So you could say, what is the adrenal gland part of, or at least what things do we know that it must be part of? And then you get things like abdomen, chromaffin system. You also get quite general things. It's part of an anatomical entity. It's part of an independent continuate. Just because all of the semantic entailments are pre-computed there. And so there's 34 other modes. And I meant to say before that all the reasoning here is based on AL-EL, which is really the most important profile for most OBO ontologies. The EL profile is really the only one that scales to a lot of the OBO ontologies, and it fits pretty well with the type of semantic graph that we're building for like anatomy or gene ontology. You could do a little bit more complicated query, which cell types are parts of which organs in the abdomen. And so it gets a little bit more complicated, but it's still, at least the query triples match your sort of graph perspective. Something that's a subclass of the cell ontology. Cell, what's defined up here. Everything in OBO has a numeric identifier, so it can be nice to kind of just define prefixes for the different terms and use them in a query. And so cell's part of an organ, and the organ's part of the abdomen. So we get things like mesonephric podocyte, it's part of the mesonephros, splenic fibroblasts are part of the spleen. So 387 other rows for that query. Or you can also use Ubergraph to check entailments. Just make sure, query over Uberon and see, are there any bone elements which are not part of the skeletal system? And hopefully the answer will be false. And so that works out. But this being able to do things like filter not exist and sparkle is really handy. And so those queries kind of make use of the fully entailed graph that has all those redundant, the full ontology closure. So there's another graph in the database that we call the non-redundant graph. So this would be the case if you want to use the inferred knowledge graph but traverse it more incrementally. And so it contains only the so-called direct edges. And we have some rules that define what we mean by what's a direct edge. Basically, we take the fully inferred closure graph and then remove things that are redundant. So something's redundant if it could be recapitulated by a transitive sparkle property path. So if A is a subclass of B and B is a subclass of C, we were going to throw out the edge that A is a subclass of C. And then make sure that any relations are to the most specific object and are coming from the most general subjects. And also you always use the most specific predicate. So that kind of pares down the graph into the type of graph that might be useful for traversing, like ontology browsing UI or relationships you might want to see in a term info panel or something like that. So this is done with a data log script using the Souffle tool, which is a really great tool for working with knowledge graphs. And so just an example of what's in this non-redundant graph. So if you do a query for the term I from Uberon, these are all the one hop nodes from I in the non-redundant graph. So you'll see things, it's some class of sense organ, it's part of the visual system, overlaps the nervous system. So it's generally kind of the most specific facts about I. You'll see some things that are a little bit redundant when they're property paths. So it's part of the visual system, and the visual system is capable of visual perception. Then you will have an edge because we have a property path, a property chain defined in RO. There's also a direct part of structure that is capable of edge from I to visual perception. And so that's not taken out because it would involve you working with property chain axioms in your Sparkle query, which sort of is a bit too extra complication. So the things that are kind of considered redundant are more like simple transitivity. So it's part of the visual system, but we don't, for example, have the die as part of the body. And so just to contrast this with what's in the full closure graph, all those same nodes have all of these edges between them in the full closure graph. Actually, if you had done a query for all of the nodes that are reachable by one hop from the term I in the closure graph, it's something about 10,000 edges. So there's quite a lot of inferred relations. And so just some specifics about, I already mentioned that it has about 53 ontologies there, including some of the big ones from OO, like KEBI, NCBI taxon, and the protein ontology. This is especially useful because these are things that are, take several minutes to download and load into Protege and run a query over. So if you just want to do a quick query over any of these ontologies, Ubergraph is always online and ready for you to submit a query to it. So you could get, all of the subclasses, all of the terms that are inside, Mammalia or something for the NCBI taxon. It should be quick to do. So there's about 500 million triples in it right now. And a lot of that is the relation graph computation. So more than 300 million. It takes about 4 hours to compute that. And then another hour to then prune it back to make that non-redundant relation graph. And so all of this is done with a a makefile workflow, which is in an open source repository here. And all the tools, there's a Docker image that contains all the tools used to do the build. So you can modify it and create your own if you like. And so it's running right now in a Blazegraph triple store here at Lindsay. And so you can use it just via the Sparkle endpoint. You can submit Sparkle queries from software or through something like the YasGUI query interface. So that's this free online tool which you can query any Sparkle endpoint from. It's also integrated into the Ontology Access Kit, which Chris Mungle spoke about a couple of weeks ago. And so Ubergraph is an option on several of the Oak commands. You can, for example, do a visualization of subclass and part of relationships from a Go term, like your photoreceptor outer segment, and get back an image directly. You can also download Ubergraph yourself and run it locally or do whatever you want with it. The full database is available as an mquads file. And there are some simplified tables for very fast parsing if you like to use those. So some of the users right now that we can use in Ubergraph include the Biomedical Data Translator Program, which is something that a few different OBO folks are involved in. And we here at Rincy, we have a couple projects that are part of this. So the data translator is developing this federated knowledge system, integrating existing data sets and with the idea to kind of support query answering and supporting translational research. And so a lot of the different data sources that are in Translator use OBO terms to describe what they're talking about. And so Ubergraph kind of provides the background knowledge that's in the ontologies that can be added into the federated graph. That if some term is talking about different anatomy terms, it's helpful to have the ontological relationships between those terms, also being part of the system. And so, as also part of the translator support, Ubergraph includes BioLink model categories for OBO ontology classes based on mappings that are in the BioLink model. So this is a project that provides a sort of biological schema that's a little bit different from an ontology, but kind of used for data modeling in bioinformatics projects. Some of the ontology projects are using Ubergraph quite a bit, especially Mondo, which is a pretty big ontology, which can be challenging to work with, on your local system. And it really helps in just having Ubergraph online and do some initial quality control exploration. And then, sometimes these are prototyped there, but then maybe edited somewhat to run within the Mondo build pipeline just to check, maybe certain terms shouldn't be subclass of others, or, any number of kind of graph checks. The HubMap group has built some nice tools on top of Ubergraph, this kind of spreadsheet-based workflow. So they have a group of experts who are not really ontology editors, but instead provide expected relationships, for example, like between cell terms and anatomy terms, like kidney cell types. And they have a system that they were able to develop pretty quickly that's kind of provides this feedback loop to see whether a relation that someone expects is in Ubergraph, meaning like it might not be easy to see in the ontology maybe because it's implied via a chain of various axioms, but they can kind of just quickly check to see if something that they think ought to be entailed is entailed. And so they might check for whether some particular cell is part of the retina, or are, if not, are there other relationships between those two terms that the expert could provide some feedback on. And so we're going to kind of take a second to talk about this idea of the going back to that OBO mission statement about I mentioned like interoperability early on, and so Nico has a proposal that he's put to OBO to sort of take more directly the mission that the OBO domain ontologies should be combined into be usable at least as some kind of grand union OBO ontology. He called this GUOBO, and so utilize the best practices we've been working on that we've been talking about over the last few weeks, and all these computational workflows. And all that builds toward this approach where we have this decentralized development, but we're kind of creating a single ontology for biology and biomedicine, so that all these things can be used as puzzle pieces and different modules that you plug together that you can use as one coherent ontology. And so it kind of connects back with the dashboard idea as well from, I think that was last week, that we want things to be kind of computationally actionable and automatically testable. So we have had this notion in OBO for a while of the sort of the OBO foundry ontologies, which have been carefully reviewed, and then other kind of OBO member ontologies. But that was kind of one of the early approaches in OBO. But we haven't really focused on that review aspect of it for quite a while now. And so it's sort of a new idea is that how can people find, what are the reference ontologies that are the ones that are meant to be reused widely compared to some others that are maybe more project based. And so, the idea is that there would be the domain reference ontologies would be the ones that fit together logically into this GUOBO. And the ones that are incompatible with GUOBO are just the OBO. They use the OBO infrastructure, but aren't part of this sort of unified logical structure that people use together. And so, Ubergraph, now it kind of facilitates testing of this GUOBO. It's kind of a prototype of this idea. I think it's built regularly and gives you a unified graph that can be queried to check consequences of inferences across all these ontologies together. And so it reveals integration problems. Like, for example, there was an issue someone opened on Ubergraph repository. Why does the cell ontology T cell, a mature T cell, why does it have a direct superclass material anatomical entity? That's kind of weird. It's already a subclass of T cell, and so it has this really broad term also as a direct superclass. And so, the reason is that there's a domain axiom on this relation has plasma membrane part, and that term happens to use that relation in its definition. And so that gets inferred. But what it points to is that for whatever reason, we're missing a connection that, if a mature T cell is a material anatomical entity, probably, all the other cells ought to be. So we're missing a connection at the top there that relation really ought to be at the top of the cell ontology. And so there's a lot of things that like this that you kind of notice when you're looking at all the ontologies together and with the reasoning results. And so in the future, if we get to this sort of GUOBO idea, a triple store like Ubergraph, could be one manifestation of the GUOBO. Might not be Ubergraph itself, but maybe there's one that represents the GUOBO unification. So some of the challenges that we've had in building Ubergraph involve, for one thing, logical incompatibility. So we strive for that unified ontology, but it doesn't always work. And just a couple of years ago, it was much more challenging than it is now. So a lot of problems that we had have been solved. So we realized that when you merge several ontologies together, we often ran into all these unsatisfiable classes when we ran the reasoner. And a lot of it was because we have these procedures that involve extracting bits and pieces from different ontologies as an import module. Like if gene ontology is using Uberon for anatomy, it runs an extraction procedure and gets a little snippet. But then that's sort of, one particular release of Uberon, and then another ontology might use a different release of Uberon. So when you merge these together, they might be incompatible. And so in the meantime, we've developed some different practices involving these, we call these base files, which are releases that have only the axioms that are being developed by a particular ontology project. So that it provides a more modular puzzle piece that you can combine together without having these stale axioms that you might have saved when you did your import process. And so just kind of taking that approach has solved a lot of these issues. And so now in the Ubergraph repo, we have we build a bunch of the ontologies and check their logical compatibility on a daily basis. One thing that we're still kind of working on is unintended logical inferences. So because when you combine different ontologies together, all of these axioms are global statements. And so, gene ontology references Kebi chemicals, and sometimes Kebi will change the hierarchy of chemicals, and that of course changes the hierarchy of the Go terms that are built on them. And so, sometimes these changes are not vetted. Or another aspect of it is that some ontologies might depend on a more rich reasoning profile, like if an ontology is a bit smaller and they're able to use the Hermit reasoner, which is more feature rich, they might need that to compute their hierarchy. And so when we run Ubergraph, it's only using the EL profile, so some of that hierarchy might get lost. So we're working on some newer strategies to maybe still publish only the axioms from a certain ontology, but include its inferred hierarchy within it. I think that maybe is a bit hard to follow if you haven't been trying to sort out these problems for a while. But there's a lot of little technical issues with trying to combine sort of loosely connected ontology projects. Another challenge is scaling, which hasn't really been much of a challenge so far, but it might be in the future. So the relation graph expansion is pretty big. So we're taking this sort of full materialization approach because it really greatly simplifies Sparkle queries, and it really is very handy. But right now it's about 6 times the size of the input ontologies, which is, I think, fine for now. And maybe really won't become a problem. Sometimes it would be nice to have faster queries. Some things are fast in Blazegraph and some things aren't. And so, but the nice thing about RDF databases is it's fairly easy to test out different triple stars. We're probably doing that in the near future. So so thank you for having me. And I just wanted to thank some of the folks that contributed to Ubergraph directly and our funding from NIH. And that's it.
Thanks, Jim. That was really great. There's so much cool stuff here that I haven't had so much of a view on before. So we have time for maybe a question or two, and then Nico, you need to jump in when it's time for you to start your SISM presentation. So and maybe a quick question or two.
I have a question.
Mm-hmm.
So
go ahead.
Yeah, so Jim, what's the thought that you're not including the disease ontology in this?
That Ubergraph so far has been kind of driven by a bit organically. So there isn't really a reason not to have, I guess disease ontology is not in there, but most of the projects I work with use Mondo, and so that was kind of initial focus, but there's no reason not to put it in. I don't have a great answer, I guess, because it's been more based on what people ask for.
Okay. I'm actually working on the project merging disease ontology and the Mondo and HPO. So I think I will reach out to you and we can discuss more.
Okay.
And the other things is like the scaling. Is there any thoughts on federated, like a parallel search or things like that to scale?
Do you have maybe more instances, you mean?
Yeah, just to use the parallel computing from other fields to experiment in the graph database.
Yeah, BlazeGraph itself is fairly parallelized, and so it does use quite a few CPUs when answering queries. But I think that I don't know. I feel like the scaling issues with triple stores are a lot to do with their query optimization capabilities, and so I think I'll probably just test some other triple stores. I really don't have a problem with BlazeGraph, except in terms of queries that involve aggregation, like counting large results. That can be quite slow, but kind of more like selective, like exploration queries are pretty fast.
Cool. Let's turn it over to Nico now, and more questions for Jim. Ask in the SoapUp chat, please. So take it away, Nico.
All right, thank you. So I will skip through some of the slides a little bit because we are a bit later in the hours now. But if you're interested in getting a more kind of comprehensive, slow and gentle version of this talk, you can go and check out the presentation I gave as part of the CCB series Harvard seminar, which is basically a long version of this talk. But I will just go a bit through the motivations and thoughts here. So I'm going to present on the SASM standard, which is basically a standard for representing standardized mappings for ontologies, controlled vocabularies, and database entities. So just a piece of motivation. So generally, oversimplified picture. When we are in a process of data generation, we may have different institutions generating various disparate data silo, and one day, the day of reckoning comes, the grant holders ask for it, the requirements of the field ask for it, and they are telling you, we all need to standardize, we need to verify our information. And what happens in these kind of situations is because this kind of standardization happens usually in a very bottom-up manner, is that various such bubbles start emerging. So, for example, it may be the case that these two institutions down here use the Uberon anatomy ontology to standardize their anatomy data, creating a semantic space that encompasses basically Uberon and its interpretation of anatomy. This institution down here may go and adopt the foundational model of anatomy instead for their standardizing their anatomy data. And this other institution here may either not know anything about Uberon or FMA, or just feel that it's better represented by its own in-house development. So this kind of process will then lead basically to three different semantic spaces emerging. Which is a super standard part of our, in the biomedical field, particular scientific standardization procedure. Now, the problem is not only is it extremely hard to adopt an ontology, you have a lot of let's say data maybe in natural language, you're having a more kind of tagging type approach. And you've now went through this painful task of saying, okay, I'm going to use an ontology to standardize my data, but it is even hard to keep on maintaining this standardization, because, for example, you may have a group that is using Uberon saying, I need for my particular use case these 250 terms. And then another group says, no, these terms do not belong here. They are not really in scope for this ontology, and so on and so on. You can see standardization is never going to stop being also a difficult process. There may be even some disagreements in terms of how classification works. So it's expensive to adopt a standard, and it is expensive to keep on using it. So this beautiful vision that we all kind of have in our hearts in OBO, and that I will defend for as long as I can, that in the end people will see the light and adopt, let's say, the one best ontology for the use case, and everyone is just saying, oh, okay, no problem. If Uberon is the best, then I will switch from using whatever I was using before to Uberon. This is very unrealistic. In fact, it won't happen. So the situation is we will keep having semantic spaces that look like that, and these beautiful graphs that Jim just described to us that are so nicely, beautifully integrated in OBO internal fashion. This is very, very unlikely to ever be the case if you're looking into the wider, bigger picture of, let's say, biomedical and clinical data and information. So in order to build big knowledge graphs that include resources from different semantic spaces, we will have to provide some kind of mappings between these spaces, and cannot rely on something like a general standard ruling them all. So what is a mapping? In essence, a mapping, so basically just imagine we have like a database here on the left side where we have like one kind of record in the database that is referencing Friedreich's ataxia, maybe using the string here. Then we have another kind of data set, maybe an Excel spreadsheet, which uses an identifier from the OMOP standard vocabulary, that both refer to the concept of Friedreich's ataxia. So basically, what is an entity? First of all, an entity is a symbol, such as a class in an ontology, a code in a terminology like HICD, an enum in a data model like male, female, or something like that, or even simply a string in a controlled vocabulary that in a text field that is all intended to refer to some real world thing. And when we are talking about mappings, we mean many different things, like just trying to get people to actually define what they are talking about is already proven that there are lots of different views on what this actually means. But there are like 3, possibly many more types of mappings, I think, that make sense to distinguish. So we have mappings, for example, from strings to identifiers. In OBO, we would call this basically a synonym type thing, but there's other communities that would call this a mapping. Then we have identifier to identifier mappings, such as EFO to Mondo, and we have more complex mappings, like, for example, a DVpedia term cheese sandwich to the Wikidata terms for cheese and sandwich. So in SESAM, we are generally focused a lot on the second type here, but all of them we are considering. All right, I need to now slightly speed up, unfortunately, but the problem basically is that in real life, the mappings that are out there are very, very underspecified. So if you're looking at any like random mapping set, like this is, for example, an example of a really good mapping set, which is provided by OMOP. You can see that it lacks a lot of the kind of specificity that is needed to build a knowledge graph, like the one that Jim showed before, for example, by simply providing something like a maps to relationship. You don't know in what way is it broad, like refractory anemia with multilineage dysplasia maps to refractory anemia. They are definitely not the same thing. So it seems more that this is like a broad match kind of thing. And this kind of muddles this kind of lack of semantics and mappings makes it basically impossible to build knowledge graphs like the one that we've been talking about before. But in general, there's also no standard format to share these around and make it easy to interpret whatever the person who built them meant when they created it. Very often, a spreadsheet with 2 columns mapped to column 1, mapping column 2. And also, obviously, it's very difficult to create good mappings. If you have ever tried to map an ontology like DO or Mondo to something like ICD-10, you will know it's like a nightmare. It's really, really difficult to map these heavily precomposed concepts. And especially since the things we are mapping together are actually not semantically compatible, it's really, really difficult to figure out very often which terms are actually corresponding to the same thing and which are just named in the same way, and very, very difficult task. So the spiel is we can somehow do better. It is expensive to produce mappings, so we should share these mappings. We have this sort of mission for us that society as a whole should not have to fund this incredible duplication of effort that we are currently having, where everyone keeps like mapping their things to something else, and the taxpayer is basically paying the same mapping 50, 60 times over and over again. We should be able to create mappings that are more useful, more interpretable with metadata, and also build a decentralized effort like what we do with OBO ontologies that allows us to share and integrate mappings together. So for SESAM, I'm just going to say two things. So the basic model of SESAM is simply a subject predicate object type statement, where we have in the predicate a mapping predicate like that we usually take from the SCORS vocabulary, exact match, broad match, narrow match, and some other specialized relationship, plus a justification. Like, for example, we say this mapping is justified by a lexical match on the label of the subject to the label of the object by a tool X, and results in a mapping with confidence 80%. There are many other kinds of mapping justifications like that. And the result, the format that we are using is basically like a TSV format that's super simple, with like a subject ID column, subject label column, predicate ID column, and so on, and a bit of metadata that we share at the top. So I'm encouraging you all to check this out a little bit. We have no time to talk about the semantics of mapping relationships and the justifications. Maybe just to say that for a given mapping, obviously we have lots of tools that are generating these mappings, but we also have heavily manual mapping curation, where we have different kinds of criteria we need to capture in order to capture the metadata well. There's a lot of documentation about that also on the SESAM pages. All right, I'm just going to skip over this part as well. So the basic vision is that everyone, let's say, that produces mappings, produces them in a standard format. We can reuse each other's mappings, we can reconcile them, we can integrate them, and we save a lot of money by being able to do that in a standardized, understandable manner. Yeah, so I'm just not going to read the acknowledgements. We have just 1 minute left for one question maybe, and then that's it for today.
Mm-hmm. One question. I don't know, Ravi had some questions in the chat. Would you like to have the final question here, Ravi?
I like to make two comments. In the first half of the talk, we heard a great attempt at successes. I am very happy to see multiple ontologies being able to be linked. The second talk, I think, Nico, you just alerted us to the difficulties of integrating. Now my question is, in future, if we don't want to proliferate these costly cleanup operations later, just as you do in software languages, a controlled vocabulary by not allowing and just giving error at the time of construction or development of software, similarly, are there going to be attempts that filter out things that will cause ambiguities in future? So some super referential engine or some logic checking algorithm which says, no, you don't go on this path, otherwise you will have 1,000 errors later in cleaning up. Some such idea will have to come in for us to integrate vocabularies and terms and controlled languages to integrated ontologies.
Yep. So this relates much more to what Jim was saying before, and to the very hopeful vision of more and more people in the open space trying to build interoperable ontologies using these tools that we have developed, and building what we call like continuous integration systems that make sure that we stay interoperable at all times with all the other dependent ontologies that we have. I think, though, that in reality, we will have to live with the fact that many, many vocabularies will be used and even more widely used, let's say like SNOMED, outside of open science space, which we will never fully logically integrate with the stuff that we are doing. We will always have to do a little bit of a compromise, map those terms into our internally consistent state, and then shift data depending on the use case from the one space into the other space. And if the mappings are good, we can shift the data back as well and make sure that the data is at least consistent with that. But the integration, the wider integration, I think, is probably not ever going to happen. Sorry about that.
I love listening to Nico's idealism and his pragmatism on alternate days. All right. Thanks, everybody. Thanks, Nico, and thanks, Jim, for your great presentations. And thanks for all the comments and questions in the chat. Next week, we're going to wrap up the kind of first half of the Ontology Summit with the panel, kind of discussing, summarizing this last several weeks. And then in the following weeks, we'll kind of move on beyond the bio domain into the wider domains. So thank you all for coming today. And I'm really hoping to see you